Right now, galaxies at the edge of the universe are rotating wrong, and physicists have no idea why. For 50 years, we have measured stars orbiting their galactic centres at speeds that should rip those galaxies apart. They move too fast. Gravity should be weaker out there, but it is not. The numbers break every equation we have. Either Einstein's theory of gravity collapses at large scales, or 95% of the universe is made of something invisible that we have never detected. Both options are terrifying. We will explore the observations that shattered our confidence, examine why our most successful theory might be fundamentally wrong, and reveal what it means when the force holding reality together stops making sense. If you are ready to question everything you thought you knew about gravity, hit that like button and subscribe. Prepare yourselves. We begin. In 1970, astronomer Vera Rubin pointed a telescope at the Andromeda Galaxy and measured something impossible. She tracked the velocity of stars orbiting at Andromeda's outer edge, expecting them to move slowly like planets in our solar system. Neptune crawls along at 3 miles per second because the Sun's gravity weakens with distance. Mars races at 15 miles per second because it sits closer. This is Kepler's law. Every object in astronomy obeys it, except galaxies do not. Rubin found that stars at Andromeda's edge move just as fast as stars near the centre. The rotation curve, a graph of velocity versus distance, should decline smoothly as you move outward. Hers stayed flat. Perfectly, impossibly flat. Stars 200,000 light-years from the galactic core moved at 200 kilometers per second. Stars 10,000 light-years from the core also moved at 200 kilometers per second. The curve did not drop. It did not even bend. She checked her instruments. She recalibrated. She observed dozens more galaxies. Spiral after spiral showed the same pattern. The outer regions spun far too fast. At those speeds, galaxies should tear themselves apart in a few million years. Centrifugal force should fling stars into intergalactic space like water, flying off a spinning wheel. But galaxies are billions of years old. They are stable. Something is holding them together with gravity that should not exist. The mathematics were brutal. Rubin calculated the mass needed to generate enough gravity to keep those outer stars bound. The number came out 6 times higher than all the visible matter combined. Every star, every gas cloud, every speck of dust she could see accounted for less than 20% of the gravitational pull. The other 80% was missing. You could add up every photon of light emitted by Andromeda, convert it to mass using every known stellar process, and you would still be short by a factor of 6. Other astronomers confirmed her results. Radio telescopes mapped hydrogen gas extending beyond the visible stars. That gas also moved too fast. X-ray observations showed hot gas in galaxy clusters behaving the same way. The anomaly was not limited to one type of object or one wavelength of light. It was universal. Every galaxy ever measured rotated wrong. The expected curve, declining smoothly according to Newton and Kepler, appeared nowhere in nature. The observed curve, flat and defiant, appeared everywhere. This was not a minor discrepancy. This was not experimental error. This was gravity failing at galactic scales. Either our understanding of how gravity works across hundreds of thousands of light years is completely wrong, or the universe is dominated by matter that emits no light and interacts with nothing except through gravitational force. Rubin's flat rotation curves became the single most important unsolved problem in astrophysics. They remain unsolved today. The implications were staggering. If visible matter makes up only 15% of a galaxy's mass, then everything we see, stars, nebulae, planets, is just foam on an invisible ocean. The real structure of galaxies is hidden. We're observing the bright tip of a dark iceberg, inferring the bulk below only through its gravitational shadow. We do not know what that bulk is made of. We do not know why it clumps around galaxies. We only know it is there because without it, galaxies should not exist. Therefore, the crisis began not with exotic theory, but with simple measurement. Point a telescope at a galaxy. Measure how fast its stars move. Compare that to how fast they should move. Watch the numbers diverge into impossibility. The solution physicists proposed sounded like science fiction. They invented matter that cannot be seen, cannot be touched, and passes through normal matter without interaction. They called it dark matter, and they claimed it outweighs everything visible by a ratio of 6 to 1. Every atom in your body, every star in the sky, Every galaxy ever photographed represents a tiny minority of the universe's mass. The rest is dark. Dark matter does not emit light at any wavelength. It does not absorb light. It does not reflect light. Shine a flashlight through a cloud of dark matter, and the beam passes straight through as if nothing were there. This is not because dark matter is thin or sparse. A dark matter particle could pass directly through the Earth and emerge on the other side without slowing down. It interacts only through gravity, making it fundamentally invisible to every instrument humans have built except those that measure gravitational effects. The properties required for dark matter are extreme. It must be cold, meaning the particles move slowly compared to the speed of light. Hot dark matter made of fast-moving particles would not clump around galaxies. It would spread out uniformly, failing to explain rotation curves. So the particles must be cold and massive enough to generate significant gravity, but not so massive they collapse into black holes. They must be stable, lasting billions of years without decaying, and they must be abundant, filling every galaxy with a halo of invisible mass extending far beyond the visible stars. Physicists proposed candidates. Weakly interacting massive particles called WIMPs became the leading hypothesis. These hypothetical particles would have masses tens or hundreds of times heavier than a proton, but interact with normal matter only through the weak nuclear force and gravity. Billions of them pass through your body every second, and you feel nothing. Another candidate, axions, would be far lighter, barely more massive than a photon, but exist in such staggering numbers they would dominate the universe's mass budget. Experiments were built to catch these particles. Detectors deep underground, shielded from cosmic rays, waited for a dark matter particle to collide with a xenon atom or a germanium crystal. The collision would release a tiny flash of light or a small amount of heat. Decades passed. The detectors saw nothing. Sensitivity improved by factors of 1,000. Still nothing. Either dark matter interacts even more weakly than predicted, or it does not exist in the form we expect, or it does not exist at all. Despite the lack of direct detection, dark matter explained more than just rotation curves. It explained how galaxies form in the first place. In the early universe, normal matter was too hot and too affected by radiation pressure to collapse into clumps. Dark matter, unaffected by light, could collapse first, creating gravitational wells that pulled normal matter in later. Simulations of structure formation using dark matter produced a cosmic web of filaments and clusters that closely matched observations. Without dark matter, those simulations failed. Galaxies did not form fast enough or in the right places. Dark matter also explained gravitational lensing. When light from a distant galaxy passes near a massive object, gravity bends the light's path, distorting the background galaxy's image into arcs or multiple images. The amount of bending reveals how much mass is present. Observations of galaxy clusters showed far more lensing than visible matter could produce. The missing mass inferred from lensing matched the missing mass inferred from rotation curves and from cluster dynamics. 3 independent measurements pointed to the same invisible component. But questions remained. Why does dark matter clump around galaxies in exactly the right way to produce flat rotation curves? Why does the ratio of dark to normal matter stay roughly constant across galaxies of vastly different sizes? Why has 50 years of searching failed to detect a single dark matter particle in a laboratory? The hypothesis solved rotation curves but introduced a new mystery, arguably deeper than the one it resolved. We replaced one unknown with another. The alternative was darker still. If dark matter does not exist, then our theory of gravity is wrong, not slightly wrong, fundamentally, catastrophically wrong on scales larger than solar systems. Einstein's general relativity, tested to extraordinary precision in every other context, breaks down when applied to galaxies. This option terrified physicists because general relativity is the foundation of modern cosmology. Abandon it, and the entire structure collapses. Therefore, dark matter became the consensus not because evidence for it was strong, but because the alternative was unthinkable. The problem did not stay confined to galaxies. It spread outward to the largest structures in existence, and the numbers got worse. Astronomers studying galaxy clusters, groups containing thousands of galaxies bound together by gravity, found the same mass discrepancy magnified. Visible matter accounted for even less of the total mass. The ratio shifted from 6 to 1 to 10 to 1. Something was very wrong. galaxy clusters are the most massive gravitationally bound objects in the universe. They contain trillions of stars spread across millions of light years. Between the galaxies floats hot gas, heated to tens of millions of degrees by the gravitational collapse of the cluster. This gas emits X-rays, making it detectable even though it is invisible in optical light. When astronomers added up the mass of all the stars and all the hot gas, they expected to account for most of the cluster's mass. They did not. They found 15%. The missing mass revealed itself through motion. Galaxies within clusters move at speeds over 1,000 kilometers per second. At those velocities, they should escape the cluster's gravity and fly off into space unless far more mass is present than we can see. Swiss astronomer Fritz Zwicky calculated this in 1933, decades before Vera Rubin measured rotation curves. He called the missing mass Dunkle Materie, dark matter. His colleagues dismissed him. The idea was too radical, too convenient. Zwicky died before his prediction was confirmed. Gravitational lensing provided the proof. Light from galaxies billions of light years behind a cluster bends around the cluster's gravity, creating distorted images. The amount of bending depends on total mass, visible or not. Observations showed that clusters bend light far more than their visible matter allows. The lensing maps revealed where the mass concentrates. It does not follow the galaxies. It does not follow the hot gas. It forms a smooth halo surrounding the cluster, peaking near the center, but extending far beyond the visible boundaries. Then astronomers measured the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation fills the universe uniformly, but tiny temperature fluctuations encode information about the early universe's density. The pattern of hot and cold spots depends on how much normal matter, dark matter, and dark energy existed when the universe was 380,000 years old. Satellites mapped these fluctuations with extraordinary precision. The data fit a model with 5% normal matter, 27% dark matter, and 68% dark energy. The numbers were unnervingly specific. Dark energy presented an even stranger problem. Discovered in 1998 through observations of distant supernovae, dark energy is a repulsive force causing the universe's expansion to accelerate. It behaves opposite to gravity, pushing space apart rather than pulling matter together. Its nature remains completely unknown. It might be energy inherent to empty space itself, or it might be a dynamic field that changes over time. Either way, it dominates the universe's energy budget, outweighing all matter by more than 2 to 1. Combine dark matter and dark energy, and we understand only 5% of the universe. 95% is invisible, undetectable except through gravitational effects, and unexplained by any known physics. This is not a gap in knowledge. This is an abyss. Every star, planet, and living thing exists within a thin shell of comprehensible matter, floating in an ocean of darkness. Some physicists propose that gravity weakens at cosmic scales, eliminating the need for dark energy. If gravity does not pull as strongly across billions of light years, the universe's expansion would naturally appear to accelerate without requiring a mysterious repulsive force. But these modified gravity theories struggled to match observations. They predicted different patterns in the cosmic microwave background than what satellites measured. They failed to explain the precise balance of structure formation. Every attempt to eliminate dark energy reintroduced other problems. Others suggested gravity strengthens at large scales, which would reduce the need for dark matter. If gravitational attraction is stronger than Einstein predicted when applied to galaxy clusters, less invisible mass is required to explain their dynamics. But this created conflicts with solar system tests of general relativity. Gravity behaves exactly as Einstein predicted around the Sun, around binary pulsars, and during the inspiral of merging black holes. Any modification must leave these regimes untouched, while activating only at galactic scales or beyond. The fine-tuning required seemed implausible. The observations formed a tightening noose. Rotation curves demanded extra mass in galaxies. Cluster dynamics demanded even more mass. Gravitational lensing confirmed the mass was there but invisible. The cosmic microwave background pinned down the exact ratio of components. Structure formation simulations only worked with dark matter. Every measurement agreed. Either the universe is dominated by substances we have never isolated in a laboratory, or gravity itself changes behavior depending on scale in ways that perfectly mimic invisible matter. Both options were absurd. One had to be true. In 1983, Israeli physicist Mordechai Milgram proposed something heretical. He suggested gravity itself changes at low accelerations, not because of exotic particles or hidden dimensions, but because Newton's inverse square law simply stops working when gravitational pull becomes sufficiently weak. Below a specific threshold, gravity does not weaken as fast as it should. This single modification explained galaxy rotation curves without invoking a single particle of dark matter. The threshold is absurdly small, 1/10 billionth of the acceleration you experience standing on Earth's surface. At accelerations above this value, gravity behaves exactly as Newton described. An apple falls, planets orbit, binary stars spiral inward. Everything works. But at accelerations below this threshold, in the outer regions of galaxies where stars orbit lazily through weak gravitational fields, the rules change. Gravity becomes stronger than expected, or more precisely, it stops weakening as quickly. Milgram called his theory modified Newtonian dynamics. MOND. The mathematics was simple compared to the complexity of dark matter halos. One new constant, one modified equation, and flat rotation curves emerged naturally. Feed. MOND. The distribution of visible matter in a galaxy, and it predicts the rotation curve with startling accuracy. No invisible halos, no fine-tuning, just a different law of gravity at low accelerations. The theory made precise predictions. For any galaxy, measure the distribution of stars and gas, plug it into MOND's equation, and out comes the rotation curve. Milgram tested this on dozens of galaxies. The predictions matched observations almost perfectly. The agreement was uncanny. Dark matter models required adjusting the halo's shape and density for each galaxy individually. MOND used the same equation for all of them, and succeeded. More striking, MOND predicted a relationship between a galaxy's total visible mass and its rotation speed. This relationship, called the baryonic Tully-Fisher relation, appears in observations with almost no scatter. Galaxies with twice the visible mass rotate at a predictable faster speed. Dark matter struggles to explain why this relation is so tight. Dark matter halos could have any profile, any concentration, producing different rotation speeds for the same visible mass. Yet nature chooses a precise relationship. MOND explains it automatically. The rotation speed depends only on visible mass and the acceleration threshold. No freedom, no adjustable parameters. The threshold itself has units of acceleration. 1.2 times 10 to the negative 10 meters per second squared. This number appears nowhere else in physics. It is not related to the speed of light, Planck's constant, or the gravitational constant. It simply is. Some physicists found this deeply unsatisfying. Fundamental constants should emerge from deeper principles, not be inserted by hand. Others argued that empirical facts matter more than aesthetic preferences. The threshold works, that should be enough. MOND also made a bold claim about where dark matter should not appear. In the solar system, accelerations are far above the threshold. Planets experience accelerations millions of times stronger than MOND's critical value. Therefore, MOND predicts no deviation from Newtonian gravity here. Observations confirm this. Planetary orbits follow Newton's laws exactly. No extra mass needed. No anomalous accelerations detected. MOND passes this test cleanly. But the theory faced immediate problems beyond galaxies. Galaxy clusters contain too much motion for MOND to explain using visible matter alone. Even with modified gravity, the galaxies move too fast. Milgram acknowledged this. He suggested clusters might contain ordinary matter we have not detected, perhaps in the form of faint stars or cold gas. Or perhaps MOND's formula needs adjustment at even larger scales. The theory was incomplete. The cosmic microwave background presented a worse problem. The pattern of temperature fluctuations depends on the balance of forces in the early universe. Gravity pulls matter into clumps. Radiation pressure pushes it apart. The competition creates acoustic oscillations, sound waves in the primordial plasma. These waves freeze when the universe cools enough for atoms to form, leaving an imprint on the microwave background. The pattern encodes the ratio of normal matter to dark matter. MOND offers no dark matter. The pattern should look different. It does not. Relativistic extensions of MOND attempted to fix this. Theories like tensor vector scalar gravity, TVES, or quasi-linear MOND, QMOND, embedded MOND's ideas into frameworks compatible with general relativity. These theories introduced additional fields that modify gravity's behavior at low accelerations while preserving Einstein's equations at high accelerations. They produced predictions for the cosmic microwave background closer to observations, but they added complexity. The simplicity that made MOND attractive vanished under layers of mathematical machinery. Despite its flaws, MOND refused to die. Every few years, new observations emerged that it explained better than dark matter. The theory survived because it kept working where it should work, in galaxies, and because dark matter kept failing to appear in detectors. The absence of evidence became evidence of absence. 50 years without detecting a dark matter particle, despite increasingly sensitive experiments, eroded confidence. Maybe we were searching for something that does not exist. Maybe gravity simply behaves differently than we thought, and we have been too stubborn to accept it. The war between dark matter and MOND is not polite academic disagreement. It is existential combat where only one theory can survive. Both sides have evidence, both sides have failures. Neither can deliver a knockout blow, and the tension escalates with every new observation. Dark matter's greatest strength is its universality. It explains rotation curves, galaxy cluster dynamics, gravitational lensing, structure formation, and the cosmic microwave background using a single hypothesis. One type of invisible particle distributed throughout the universe accounts for dozens of independent observations. The theory is ugly, requiring matter we cannot detect, but it is comprehensive. Add dark matter to simulations of cosmic evolution, and galaxies form in the right places at the right times. Remove it, and the simulations fail catastrophically. MOND's greatest strength is its precision. It predicts galaxy rotation curves with one equation and no adjustable parameters. Feed in the visible matter distribution, and the rotation speed emerges exactly as observed. The baryonic Tully-Fisher relation, the radial acceleration relation, the surface density threshold below which rotation curves flatten, all of these fall naturally from MOND's mathematics. Dark matter reproduces these patterns only by carefully tuning halo properties galaxy by galaxy. The tuning always works, but it feels artificial. The radial acceleration relation discovered in 2016 delivered a stunning blow to dark matter. Astronomers compiled data from 2,500 galaxies and found that the acceleration predicted by visible matter correlates perfectly with the observed acceleration at every radius. Plot one against the other, and all galaxies collapse onto a single curve. This is MOND's signature prediction. Dark matter models struggle to explain why halos would conspire to produce this exact relationship across galaxies of wildly different masses and morphologies. Dark matter advocates counter with simulations. Modern cosmological simulations using dark matter reproduce the cosmic web's large-scale structure with extraordinary fidelity. Filaments, voids, and clusters emerge naturally from gravitational collapse of dark matter, seeded by quantum fluctuations in the early universe. The simulations predict where massive galaxy clusters should exist today, and telescope surveys find them in those exact locations. MOND simulations cannot yet match this success because MOND lacks a fully developed cosmological framework. MOND advocates point to dwarf galaxies. These small, dim galaxies contain few stars but rotate faster than visible matter allows. Dark matter explains this by placing massive halos around dwarfs, but the halos must be precisely tuned. Too much dark matter, and the dwarf's rotation curve rises too steeply. Too little, and it stays too flat. MOND explains dwarf rotation curves with the same equation that works for giant spirals. No tuning required. The dwarfs simply have low enough accelerations that MOND's modification activates. Dark matter fires back with ultra-faint dwarfs. These galaxies contain only a few thousand stars but show signs of dark matter domination. Their stars move too fast for the visible mass. MOND predicts these tiny systems should barely feel the modification because their accelerations might not drop below the threshold everywhere. Yet observations suggest they are dark matter dominated. The evidence is murky. Measuring velocities in systems with so few stars is difficult. Error bars are large. Both sides claim the data supports them. The satellite plane problem haunts dark matter. The Milky Way's dwarf satellite galaxies do not distribute randomly in 3 dimensions as dark matter simulations predict. They lie in thin planes, orbiting coherently like planets around a star. Andromeda shows the same pattern. Simulations using dark matter produce random distributions. Getting satellites to align in planes requires special initial conditions or destruction of most satellites, leaving only the planar ones. MOND naturally produces planar structures because it modifies gravity in anisotropic ways depending on the direction and strength of the gravitational field. Dark matter cannot explain this easily. Dark matter counters with the missing satellites problem turned success. Early simulations predicted far more dwarf galaxies around the Milky Way than observations found. This was called the missing satellites problem, and MOND advocates used it as evidence against dark matter. Then deeper surveys discovered hundreds of ultra-faint dwarfs exactly where simulations predicted. The missing satellites were not missing, they were just too dim to see. Dark matter's prediction was vindicated. MOND struggles with galaxy clusters and must invoke unseen baryonic matter, essentially reintroducing a form of missing mass. Clusters contain hot X-ray emitting gas that outweighs the stars, but even adding this gas, MOND cannot generate enough gravity to explain cluster dynamics. Milgram proposed additional neutrinos, particles with tiny mass, might fill the gap. This feels like cheating. MOND was supposed to eliminate invisible matter, not replace one invisible component with another. Dark matter struggles with the core cusp problem. Simulations predict dark matter halos should have dense cusps at their centers, where density rises steeply. Observations of galaxy rotation curves show flat cores where density stays constant. Galaxies appear to have less dark matter in their centers than simulations predict. Dark matter advocates argue that feedback from star formation, supernova explosions, and black hole activity can blow dark matter out of galactic centers, flattening the cusps into cores. MOND advocates argue this is post hoc tuning to save the theory. Both theories require belief in something unproven. Dark matter requires belief in particles that have evaded detection for 50 years. MOND requires belief that gravity, tested exhaustively in the solar system, and with gravitational waves suddenly changes behavior at low accelerations for reasons unknown. Neither option is satisfying. Both explain some observations beautifully and fail others spectacularly. The war continues because neither side can land the final blow. Every new dataset is claimed as victory by both camps. The scientific community remains fractured, unable to reach consensus. We are stuck. In 2006, astronomers observed two galaxy clusters colliding at 4 million miles per hour. The collision, called the Bullet Cluster because of its appearance, created the most violent event witnessed in the universe since the Big Bang. And it appeared to prove dark matter exists. The Bullet Cluster sits 3.8 billion light-years away in the constellation Carina. Two massive clusters smashed together hundreds of millions of years ago. We see the aftermath. The collision separated matter into visible and invisible components in a way that should not be possible if dark matter does not exist. The visible matter, primarily hot gas between galaxies, collided and slowed. Gas clouds moving at millions of miles per hour do not pass through each other. They crash, heat up, and emit X-rays. Chandra X-ray observatory images show two enormous clouds of gas, each containing more mass than all the stars in both clusters combined, stalled at the collision point. The gas interacted electromagnetically, friction stripped momentum, and it lagged behind. But gravitational lensing revealed something else. The mass distribution inferred from how background galaxies are distorted shows two peaks that do not align with the gas. The lensing peaks sit ahead of the gas clouds, having passed through the collision point and continued moving. Something massive moved through the collision without slowing down. That something was invisible. Dark matter advocates declared victory. The observation proved that most mass in clusters is not gas or stars, but something collisionless that passes through itself without interaction. Dark matter particles, moving with the galaxies, sailed through the collision zone unimpeded because they do not collide with each other or with normal matter. The galaxies themselves, tiny compared to the spaces between them, also passed through mostly unscathed. But the gas filling the space between galaxies slammed together and stopped. The separation between visible gas and invisible mass created a clean test. If all gravitational mass were normal matter, the lensing peaks should align with the X-ray peaks. They do not. The offset is enormous, hundreds of thousands of light years. The lensing maps show gravitational mass concentrated where almost no visible matter exists. This is dark matter's signature. MOND struggled to explain this. Milgram and his supporters argue that the dynamics of cluster collisions in modified gravity are complex. During a collision, the gravitational field changes rapidly. MOND's equations, which depend on acceleration, produce different behavior in time-varying fields. Perhaps the modified gravity creates lensing effects that mimic separated mass distributions. Perhaps the interpretation of lensing in MOND frameworks differs from the interpretation in general relativity. These arguments sounded weak even to sympathetic ears. The bullet cluster became the poster child for dark matter. NASA released images showing the X-ray gas in pink and the lensing mass contours in blue. The two distributions were clearly separated. The visual was compelling. Here was direct evidence of invisible mass. You could see where it was and where it was not. Other colliding clusters were found showing similar separations. The musket ball cluster, Abel 520, the trainwreck cluster, all displayed gas lagging behind gravitational mass. The pattern repeated. Collisions systematically separated normal matter from whatever produces the gravitational lensing. The evidence mounted. But MOND advocates did not concede. They pointed out that the bullet cluster is an extreme system. Collisions at such high velocities are rare. Using one rare event to rule out a theory that works for thousands of galaxies seemed premature. They also noted that even in dark matter models, the bullet cluster is difficult to explain. Simulations rarely produce collisions with the observed geometry and velocity. The probability of witnessing such an event is low. Perhaps the bullet cluster itself is an outlier that neither theory handles well. More troubling for dark matter, detailed analysis showed the lensing signal is weaker than expected. If dark matter halos are as massive as inferred from cluster dynamics, the lensing should be stronger. The discrepancy is not fatal, but it is uncomfortable. Some researchers suggested the clusters are viewed at an unlucky angle, diluting the lensing signal. Others proposed the dark matter distribution is more complex than simple models assume. MOND supporters also highlighted the trainwreck cluster, Abel 520. This cluster shows a more complicated structure with multiple lensing peaks that do not align neatly with either the gas or the galaxies. The separation is not as clean as in the bullet cluster. If every collision produced bullet cluster-like separations, MOND would be dead. But collisions show variety. Some align well with dark matter predictions. Others are ambiguous. Attempts to model the bullet cluster in relativistic MOND frameworks like TeVS produced mixed results. Some models reproduced the lensing offset by invoking neutrinos or other non-dark matter components. Others failed entirely. The problem is that MOND was designed for equilibrium systems like rotating galaxies. Collisions are non-equilibrium, time-dependent and relativistic. Extending MOND into this regime requires assumptions that may not be valid. Dark matter's triumph was real but not absolute. The bullet cluster provided the strongest evidence to date that something collisionless and invisible dominates cluster mass. It forced MOND advocates onto the defensive, but it did not end the war. MOND still explained galaxy rotation curves better than dark matter. The bullet cluster proved dark matter exists in clusters, but it did not prove dark matter exists in galaxies. Perhaps both phenomena require different explanations. Perhaps the universe is more complicated than either theory alone can capture. In 2023, astronomers analysed 14,000 wide binary star systems in the Milky Way and found gravity deviating from Newton's predictions at exactly the acceleration threshold MOND predicts. The observation sent shockwaves through the dark matter community. This was not a distant galaxy. This was our own cosmic neighbourhood. Wide binary stars are pairs of stars orbiting each other at separations of thousands of astronomical units. 1 astronomical unit is the distance from Earth to the Sun. These binaries orbit so slowly and at such vast distances that their gravitational accelerations drop to incredibly low values, below MOND's threshold. If MOND is correct, gravity should strengthen at these separations compared to Newtonian predictions. The stars should orbit faster than Newton allows. The research team led by Kyuhyun Chai used data from the Gaia Space Telescope, which measured positions and velocities of billions of stars with unprecedented precision. They selected wide binaries with well-determined orbits and calculated the gravitational acceleration each star experiences. For accelerations above MOND's threshold, the orbital velocities matched Newtonian predictions perfectly. For accelerations below the threshold, the velocities were higher. The transition occurred exactly where MOND predicts. The effect was not subtle. Below the threshold, stars moved roughly 20% faster than Newton's inverse square law allows. The deviation matched MOND's mathematical formula within error bars. Plot the ratio of observed acceleration to predicted acceleration against the predicted acceleration itself, and the data trace MOND's curve precisely. Above the threshold, the ratio sits at 1.0. Below the threshold, it rises. This was devastating for dark matter. Wide binaries sit within the Milky Way's dark matter halo, according to standard models, but dark matter's density should be nearly uniform across the small regions occupied by individual binary systems. There is no mechanism for dark matter to boost the gravity between two stars separated by thousands of astronomical units, while leaving stars separated by hundreds of astronomical units unaffected. Dark matter cannot turn on and off based on acceleration. It simply provides extra mass. MOND, however, predicts exactly this behavior. Dark matter advocates scrambled to find alternative explanations. Some suggested the binaries are not truly isolated, but are contaminated by undetected third stars or background objects. If a faint third star orbits the binary, it would add gravitational pull, mimicking MOND's effect. But the Gaia data is precise enough to detect most contaminants. Statistical analysis showed contamination could not account for the observed deviation. The signal remained after removing suspect systems. Others proposed that the binaries are not bound but are chance alignments of unrelated stars moving through space along similar paths. If the pairs are not gravitationally bound, their relative velocities would not follow Newtonian predictions because they are not orbiting. But this explanation requires an implausible number of chance alignments. The probability that 14,000 apparent binaries are actually unrelated stars is vanishingly small. Kinematic studies confirmed most systems are genuine binaries. A more technical objection involved orbital eccentricity. Wide binaries have elongated elliptical orbits. At different points in the orbit, the stars experience different accelerations. If the orbit is highly eccentric, the instantaneous acceleration might not represent the system's true dynamics. But the analysis accounted for this. The researchers averaged over orbital phases and used statistical methods to extract the mean acceleration. The deviation persisted. MOND advocates celebrated. For decades, critics dismissed MOND as a theory that only works for galaxies where dark matter could be hiding. The wide binary results showed MOND's effect appearing locally in the solar neighbourhood, where no dark matter explanation fits comfortably. The acceleration threshold is not an arbitrary parameter. It is a physical scale where gravity's behaviour changes, and that change is now observed in multiple independent contexts. The findings were controversial. Multiple teams reanalyzed the Gaia data using different selection criteria and statistical methods. Some confirmed the deviation. Others found weaker signals or no signal at all, depending on which binaries were included. The debate turned technical, focusing on how to properly model binary populations and account for observational biases. The data are noisy. Wide binaries have uncertain distances and velocities. Extracting a 20% effect from noisy data is challenging, but the preponderance of evidence leans toward a real deviation. Independent analyses using different star catalogues and different galaxies showed similar trends. Wide binaries in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, displayed the same acceleration-dependent behaviour. The effect is not confined to one dataset or one analysis method. It appears wherever astronomers look for it. Dark matter cannot easily explain a local acceleration-dependent modification of gravity. You can add dark matter to galaxies, you can add it to clusters, but you cannot make it respond to the local gravitational acceleration between two stars. Dark matter's density is set by large-scale structure formation and evolves slowly over millions of years. It does not know what acceleration a particular binary system experiences right now. MOND explains it trivially. Gravity modifies at low accelerations. Wide binaries have low accelerations. Therefore, gravity modifies. The prediction was made in 1983. The observation arrived 40 years later. This is how science is supposed to work. Theory predicts. Observation confirms or refutes. MOND predicted. Observation confirmed. Yet the war continues. Dark matter advocates argue that one observation, even a striking one, does not overturn decades of evidence for dark matter in clusters in the cosmic microwave background. MOND advocates argue that one observation in the solar neighbourhood, where systematic errors are smallest, outweighs 100 observations in distant systems where dark matter can be invoked to explain anything. Both sides claim the high ground. Neither will surrender. On August 17, 2017, gravitational wave detectors in the United States and Italy recorded a signal that killed dozens of modified gravity theories instantly. Two neutron stars 1.3 billion light-years away spiraled into each other and merged. The collision sent ripples through space-time traveling at the speed of light. 1.7 seconds later, gamma-ray telescopes detected a burst of high-energy photons from the same location. Gravitational waves and light arrived almost simultaneously. That 1.7-second delay after traveling for 1.3 billion years meant gravitational waves move at the speed of light to within 1 part in 10 to the 15th. Gravity propagates at exactly the speed Einstein predicted. This single measurement obliterated any theory that modified how gravity waves travel through space. Many modified gravity theories attempting to eliminate dark matter or dark energy rely on additional fields or different propagation speeds for gravitational effects. Some propose that gravity moves slower than light on cosmic scales, which would change how structures form and evolve. Others suggested faster than light propagation or wavelength-dependent speeds, where different frequency gravitational waves travel at different velocities. The neutron-star merger ruled out all of these. Gravity moves at light speed, period. TeVe's, the relativistic extension of MOND that Jacob Bekenstein developed, struggled immediately. TeVe's introduces extra fields beyond the metric tensor of general relativity. These fields modify gravitational dynamics to reproduce MOND's effects in galaxies, while maintaining compatibility with cosmological observations. But the additional fields predict gravitational waves should propagate differently than Einstein's theory allows. The neutron-star merger showed they do not. Bekenstein had died 2 years before the observation. His theory, designed to save MOND from relativistic inconsistencies, could not survive the test. Modifications were proposed. Perhaps the extra fields couple to matter differently than originally thought. Perhaps the fields only affect static or slowly changing gravitational potentials, and leave wave propagation untouched. Each modification added complexity and reduced the theory's predictive power. Other theories fell harder. Scalar tensor theories, where a scalar field mediates gravitational interactions alongside the metric, generically predict gravitational waves travel slower than light. The deviation depends on the strength of the scalar field's coupling to matter. Strong coupling produces large deviations. Weak coupling produces small deviations. The neutron-star merger constrained the coupling to be absurdly weak, so weak the scalar field becomes irrelevant for almost all observable phenomena. The theory survives only by becoming indistinguishable from general relativity. Some modified gravity theories specifically designed to explain cosmic acceleration without dark energy died instantly. These theories, including certain F of R gravity models and covariant Galilean theories, modify gravity on cosmological scales to produce accelerated expansion. But the modifications change how gravitational waves propagate. The speed difference between gravity waves and light should be measurable if these theories are correct. It was not. The theories were falsified. Dark matter, by contrast, survived effortlessly. Dark matter does not modify gravity, it adds mass. General relativity remains intact. Gravitational waves propagate at light speed as Einstein predicted. The neutron-star merger was a triumph for Einstein and a disaster for modified gravity. MOND faced an existential crisis. The theory itself, as originally formulated by Milgram, is non-relativistic. It modifies Newtonian gravity, not Einstein's general relativity. MOND does not make predictions about gravitational waves because it was never extended into a full relativistic framework that everyone accepts. But to explain cosmological observations, MOND needs a relativistic version. Every relativistic extension proposed so far either conflicts with the neutron-star merger or becomes so complicated it loses the simplicity that made MOND attractive. Some MOND advocates argued the neutron-star merger does not kill MOND itself, only specific relativistic implementations. The core idea, that gravity modifies at low accelerations, remains viable. Perhaps a different relativistic extension exists that preserves MOND's successes in galaxies while predicting gravitational waves travel at light speed. The search for such a theory continues, but decades of effort have not produced a satisfactory candidate. The constraints from gravitational waves tightened with every new detection. LIGO and Virgo have now observed dozens of black hole mergers and additional neutron-star mergers. Every event confirms gravitational waves propagate at light speed within tighter and tighter error bars. Any theory predicting deviations is ruled out to higher precision with each observation. modified gravity theorists responded by retreating to more conservative modifications. Instead of changing how gravity propagates, they focus on changing gravity's strength, or adding screening mechanisms that hide modifications in high-density regions. Screening allows a theory to behave like general relativity in the solar system and around merging neutron stars while activating modifications only in low-density environments, like galaxy outskirts or cosmic voids. These theories are harder to test and harder to falsify. Chameleon gravity is one example. The modification depends on local matter density. In dense regions like Earth or the Sun, the modification shuts off, and gravity follows Einstein's equations. In the sparse outskirts of galaxies, the modification activates, potentially mimicking dark matter's effects. The theory predicts gravitational waves travel at light speed everywhere because wave propagation is not modified, only the static gravitational field changes. Synchrotron and Weinstein screening mechanisms work similarly. They allow modified gravity to hide in plain sight, evading solar system tests and gravitational wave constraints, while still affecting galactic dynamics. But these mechanisms require fine-tuning. The parameters must be set precisely to screen modifications in the right environments without screening them everywhere. The theories become baroque, festooned with conditions and special cases. Dark matter advocates argue this is desperation. Modified gravity is fragmented into a zoo of increasingly contrived theories, each designed to evade the latest constraint. Dark matter, meanwhile, remains simple. One hypothesis, one type of particle, no screening, no parameter tuning per environment, just extra mass distributed according to gravitational collapse. The theory is incomplete because we have not detected the particle, but it is conceptually clean. MOND advocates counter that dark matter is also fragmenting. Cold dark matter alone does not explain small-scale structure. Warm dark matter, self-interacting dark matter, fuzzy dark matter, sterile neutrinos, axions, each propose to fix problems in specific regimes. Dark matter is not one hypothesis. It is a family of hypotheses, each invoked when convenient. The difference is that dark matter gets credit for flexibility, while modified gravity gets criticized for complexity. The neutron-star merger did not end the debate. It shifted the battlefield. Modified gravity theories must now pass a gauntlet of tests. Match galaxy rotation curves, explain cluster dynamics, fit the cosmic microwave background, and predict gravitational waves travel at light speed. No single theory passes all tests cleanly. Dark matter passes most but requires undetected particles. MOND passes galaxies but fails clusters and cosmology. The crisis deepens because nature refuses to give a clear answer. In 1998, two teams of astronomers measured the brightness of distant supernovae and discovered the universe is accelerating. Gravity should slow cosmic expansion, pulling everything back together. Instead, expansion is speeding up. Something is pushing space apart with a repulsive force stronger than gravity's attraction. They called it dark energy, and it accounts for 68% of the universe's total energy. Dark energy is more mysterious than dark matter. At least dark matter behaves like matter. It clumps, it gravitates, it follows predictable dynamics. Dark energy does none of this. It does not clump. It does not dilute as the universe expands. Its density remains constant even as space grows, meaning more dark energy continuously comes into existence to fill new volume. This violates intuition about how energy works. The simplest explanation is that dark energy is the cosmological constant, a term Einstein added to his equations in 1917, and later called his greatest blunder. The constant represents energy inherent to empty space itself. Vacuum is not nothing. Quantum field theory predicts empty space seethes with virtual particles popping in and out of existence. These quantum fluctuations carry energy. If that energy gravitates, it would produce a cosmological constant. But the predicted value is catastrophically wrong. Quantum field theory estimates vacuum energy should be 10 to the 120 times larger than the observed dark energy density. This is the worst prediction in the history of physics. Either our calculation is fundamentally flawed, or some unknown mechanism cancels almost all vacuum energy, leaving only a tiny residual amount that drives cosmic acceleration. No one knows which. Alternative explanations propose dark energy is not constant, but a dynamic field called quintessence that changes over time. If the field's energy density decreases as the universe expands, Future acceleration could slow or even reverse. This would alter the universe's fate. Instead of expanding forever into cold darkness, the universe might eventually recollapse in a big crunch. Observations so far show no evidence dark energy is changing, but the constraints are weak. We have only measured cosmic expansion over the past 10 billion years. Dark energy could vary on longer timescales. Modified gravity offers a different solution. If gravity weakens on cosmological scales, energy component. General relativity predicts expansion should decelerate as gravity pulls matter together. If gravity is weaker than Einstein thought at distances of billions of light years, the expected deceleration would be smaller. The observed acceleration could result from misapplying Einstein's equations where they do not hold. But modified gravity faces the same problem as MOND. Any change to general relativity must preserve its successes in the solar system, around binary pulsars, and in gravitational wave propagation. The modifications must activate only at cosmological scales. This requires screening mechanisms or scale-dependent couplings that feel arbitrary. Why does gravity change behavior at billions of light years, but not at millions of light years? The theory needs an explanation for the transition scale. Some models propose gravity is stronger on small scales and weaker on large scales due to extra spatial dimensions. If the universe has more than 3 spatial dimensions, gravity could leak into these extra dimensions at large distances, diluting its strength. On small scales, gravity is confined to our 3-dimensional space and behaves normally. On cosmic scales, it spreads into extra dimensions and weakens. This could mimic dark energy's effects without requiring actual repulsive energy. String theory and brane world models explore these ideas. In these frameworks, our observable universe is a 3-dimensional surface, a brane embedded in a higher dimensional space. Gravity propagates through all dimensions while matter and light are confined to the brane. At short distances, gravity appears 3-dimensional because it has not had space to spread into extra dimensions. At long distances, it spreads and weakens. The mathematics are elegant, but the predictions are vague. Extra dimensions have not been detected. Combining dark matter and dark energy creates an absurd picture. 95% of the universe consists of substances we have never isolated. Dark matter outweighs normal matter by 6 to 1. Dark energy outweighs everything else by more than 2 to 1. The universe is dominated by unknowns. Every star, planet, and atom is a rounding error in the cosmic energy budget. Some physicists find this unacceptable. The standard model of cosmology, lambda-cold dark matter, is sometimes called the concordance model because it fits many observations. But it is concordance built on ignorance. We agree on a model that requires invoking 2 mysterious components whose nature remains completely unexplained. This is not understanding. This is parametrizing ignorance. Others argue the situation is not as bad as it sounds. Dark matter behaves predictably even if we do not know what it is made of. Dark energy behaves like a cosmological constant even if we do not know why. The model makes testable predictions. Simulations reproduce observed structure. The cosmic microwave background fits. Galaxy formation works. Ignorance of fundamental nature does not prevent practical success. But eliminating dark energy by modifying gravity reintroduces the need for dark matter in most frameworks. Observations of galaxy clusters and the cosmic microwave background cannot be explained by modified gravity alone. Some mass beyond visible matter is required. Similarly, eliminating dark matter by using MOND reintroduces problems with clusters and cosmology that might require dark energy or other modifications. No single change fixes everything. A few radical proposals attempt to eliminate both. Emergent gravity theories suggest gravity is not a fundamental force, but an emergent phenomenon arising from thermodynamic properties of space-time. In these models, dark matter and dark energy are illusions created by misunderstanding gravity's true nature. The theories are speculative and lack detailed predictions. They remain on the fringe of physics, intriguing but unproven. The cosmological constant problem, why vacuum energy is so much smaller than predicted, remains unsolved. Some invoke the anthropic principle. If vacuum energy were much larger, the universe would expand so rapidly that galaxies could not form. Intelligent observers could not exist. We observe a small cosmological constant because only universes with small values allow observers to exist. This explanation is philosophically unsatisfying. It replaces a physics question with a selection effect, but it may be correct. The future of cosmology depends on resolving these mysteries. Experiments searching for dark matter particles continue with increasing sensitivity. Gravitational wave observatories will detect more mergers, constraining modified gravity theories further. Surveys will map the universe's structure in unprecedented detail, testing whether dark energy is constant or evolving. Within a decade, one paradigm might collapse, or we might confirm we truly understand only 5% of reality. The edge of the universe is not just distant, it is incomprehensible. Gravity appears to weaken or behave differently. Matter we cannot see dominates structure. Energy we cannot explain drives acceleration. We measure effects but do not understand causes. Every answer leads to deeper questions. We are cosmically blind, fumbling in darkness, trying to reconstruct reality from shadows. Every solution to the gravity problem creates new impossibilities. Accept dark matter, and you must believe in particles that have hidden from every detector for half a century, despite humanity's most sophisticated experiments searching underground, in space, and at particle accelerators. Accept MOND, and you must believe Einstein's most successful theory breaks down at low accelerations for reasons unknown, requiring a fundamental constant that appears nowhere else in physics. Accept both are partly right, and you fracture reality into regimes where different rules apply with no deeper principle explaining why. The search for dark matter particles has become desperate. Detectors filled with liquid xenon sit 2 kilometers underground in abandoned mines, shielded from cosmic rays by solid rock. The logic is simple. If dark matter fills the galaxy, billions of particles pass through Earth every second. Occasionally, one should collide with a xenon nucleus, producing a tiny flash of light. Decades of searching have found nothing. Sensitivity has improved by factors of 10,000. The detectors now see individual nuclear recoils from background radiation. Still, no dark matter. The Lux-Zeppelin experiment, the most sensitive detector ever built, began operations in 2021. It contains 10 tons of liquid xenon monitored by hundreds of photomultiplier tubes. If WIMPs exist in the mass range between 10 and 1,000 times a proton mass, Lux-Zeppelin should detect dozens of collisions per year. Years have passed. The detector sees background noise and nothing else. The parameter space where dark matter could hide is shrinking. Particle accelerators offer another search method. The Large Hadron Collider smashes protons together at nearly light speed, recreating conditions from the early universe. If dark matter particles can be produced in high-energy collisions, they would appear as missing energy. Detectors measure all the particles flying out from each collision and add up their energy. If the total is less than the energy put in, something invisible carried away the difference. Thousands of collisions have been analysed. No consistent missing energy signal has appeared. Axions, the lighter dark matter candidate, require different experiments. Axions should convert into photons when passing through strong magnetic fields. Experiments like ADMX, the Axion Dark Matter Experiment, use powerful magnets and sensitive microwave receivers to search for this conversion. The detector scans frequencies corresponding to different axion masses. After decades of searching, most of the predicted mass range has been excluded. If axions exist, they must be in a narrow remaining window or have properties different from predictions. Some physicists propose dark matter interacts even more weakly than WIMPs, making direct detection impossible with current technology. Others suggest dark matter is not a particle, but a macroscopic object like primordial black holes formed in the early universe. These black holes would be microscopic, smaller than atoms but more massive than mountains. They would gravitationally lens background stars as they pass in front of them. Surveys have searched for these lensing events. A few candidates exist, but not enough to account for all dark matter. The absence of detection does not prove dark matter does not exist. It proves we do not know what we are looking for. Dark matter could be any of dozens of hypothetical particles or objects, each requiring different detection methods. The search continues, but confidence erodes with every null result. 50 years without detection is not proof of absence, but it is not encouraging. MOND faces different problems. The theory works brilliantly for isolated galaxies, but fails for systems where galaxies interact. Galaxy clusters contain too much motion for MOND's modified gravity to explain using visible matter alone. Milgram acknowledged this from the beginning and suggested clusters might contain additional non-dark matter mass. Perhaps neutrinos with small but non-zero mass. Perhaps cold molecular gas clouds too faint to detect. These components would not be dark matter in the sense of exotic particles, but they are still unseen mass invoked to save the theory. The cosmic microwave background remains MOND's greatest challenge. The precise between gravity pulling matter into clumps and radiation pressure pushing it apart in the early universe. Dark matter provides extra gravity that shapes this pattern. MOND offers no equivalent. Relativistic extensions like TEAS add fields that partially mimic dark matter's effects, but the fit is not as clean as standard cosmology achieves. Observations of gravitational lensing by galaxy clusters create additional problems. The amount of lensing measures total mass. MOND predicts lensing based on visible matter plus modified gravity. The predictions consistently underestimate observed lensing by factors of 2 or more. Either MOND is wrong, or clusters contain substantial unseen mass, which defeats MOND's purpose. Yet MOND refuses to die because it keeps predicting observations that dark matter models struggle to explain. The baryonic Tully-Fisher relation, linking galaxy mass to rotation speed, holds across 5 orders of magnitude in mass with almost no scatter. Dark matter models reproduce this only by assuming dark matter halos have precisely tuned properties that correlate perfectly with visible matter. Why would invisible and visible matter conspire to produce such a tight relationship? MOND explains it automatically, shows that at every radius in every galaxy, observed acceleration. This is MOND's signature. Dark matter models reproduce it only by fine-tuning halo profiles individually for each like epicycles added to preserve a failing theory. Some researchers propose hybrid models combining dark matter and modified gravity. Perhaps galaxies contain some dark matter, but less than standard models require, and gravity also modifies at low accelerations. This approach explains galaxy rotation curves with less dark matter, explains clusters with the remaining dark matter, and preserves MOND's successes. But hybrid models are complex. They require both an unknown particle and a modification to gravity. The simplicity of both original theories is lost. The community remains fractured. Conferences feature heated debates where neither side convinces the other. Dark matter advocates point to cosmological successes and the bullet cluster. MOND advocates point to galaxy predictions and the lack of particle detection. Both sides accuse the other of ignoring inconvenient data. Both are partly right. Younger physicists entering the field face a choice: commit to dark matter and accept that 50 years of null results might extend to 100. Commit to MOND and accept that cosmological problems might never be solved cleanly. Or remain agnostic and work on observations, letting future data decide. Many choose the third option. The data are improving faster than theory. Perhaps nature will reveal her hand before the next generation retires. What is certain is that our picture of the universe is incomplete. Galaxies rotate wrong, clusters move wrong, the cosmos accelerates wrong. Every large-scale observation conflicts with the physics we have tested locally. Either we are surrounded by substances we cannot detect, or the laws of physics change depending on where and how we measure them. Both options are disturbing. Both suggest we understand far less than we thought. The edge of the universe is where our knowledge ends. Not at some distant horizon measured in billions of light years, but at the boundary between what we can test in laboratories and what we infer from astronomical observations. Gravity works perfectly when we measure it on Earth, around the Sun, in binary pulsars, and in merging black holes. It fails when we apply those same laws to galaxies and clusters. Something is wrong. We do not know what. We do not know why. We are trapped in our ignorance, measuring effects we cannot explain, proposing entities we cannot find, and modifying theories in ways that feel arbitrary. The universe is not obligated to make sense to us. It simply is. And what it is remains, after a century of effort, profoundly mysterious.